Welcome to Track 18. This session is labeled Tall Buildings, Other Issues. And as I looked through the subject matter, it appeared that we could call this Design and Engineering Tools to Remake Mumbai. And so I'm pleased to be participating in several sessions today that focus on technical issues. And we have three lively and dynamic speakers that are going to share some of their best practices with us. My name is Mark Garland. I'm from Willis Building, Toronto. And actually, just a footnote on Toronto, I'm fortunate to live in one of the bright economic places in North America. The rest of the U.S. and the United States seems to be a bit on its ear. So I'm happy to be in Canada. Our next speaker, who is Clive Robinson. He's a product manager for Tekla Corporation in Finland with a lot of experience in the structural steel industry and specializes in the interoperability between Tekla structures and other software systems. Take it away, Clive.
Thank you, Mark. Okay, as I said, my name is Clive Robinson. I work for the Tekla Corporation. Tekla is quite a big organisation. We'll go through some details in a minute. I've been asked to put together a presentation on a modern vehicle for transferring structural information with BIM. BIM being Building Information Modelling. We call it the Tekla Virtual Island. There's a number of projects you can see on there. You may recognise a few of them, obviously the Burj Dubai, the Burj Khalifa, right the way down to a number of different structures. Again, with the Singapore World Financial Center. On the Burj Dubai, the only part that Tekla Structures is actually used on is the very top portion, the steel portion. But we do have a multi-material mix of all the different projects, going to some quite small projects around the world. To go through the agenda, first thing we're going to be looking at is going to be design information requirements, linking of best-of-breed applications, model-based information review, and some sample projects. Mark did ask me before of what Tekla actually does. Well, Tekla is actually a software house. We produce the tools that our clients use. And the projects you actually see today will be a number of projects all produced by our different clients. So what's it all about? Really, it's a case of using BIM. How did we get from the old sleepy way of working to the modern projects? The building on the right is obviously the Shanghai World Financial Center, and again, we'll be looking at that in more detail. Just a very quick overview of Tekla. People in the room may not have heard of Tekla. The Tekla Corporation, formed in 1966. We employ about 460 people worldwide. We have our own offices in 15 countries. Some countries we have more than one office. We have 30 resellers and partners around the world, and we have clients in 92 countries. We have offices right the way across, as I was saying, from the US right the way through to Japan. A very quick overview of design information requirements and what engineers get involved with. Well, I assume most people in the room are engineers anyway, so you probably all know this information. But obviously engineers get involved in preparing schemes. It's really the transfer of information, the transfer of drawings, etc. They also look at the transfer of structural design intent, calculations on stability, fire engineering, really drawing specification quantities, explaining how the stability is going to be achieved in a building. Engineers also look after change management. Is all the design information concurrent and coordinated? In other words, does the plan have the same information as elevations and sections? Again, they get involved with requests for further information and resolving this information requirement. They get involved with checking, but it's not only their own checking, it's the design team members' checking work. It may be an MEP engineer's information and class checking between the different environments. It should also be remembered that every building is unique. There's no prototypes. It's not like a car when you want to make a car, so you make a prototype before you make thousands. Every building is normally unique. It's only built once. And using BIM technology, you're building the prototype in the memory of the computer for the very first time. But the bottom line is all about money. Everybody needs to make money. So schemes need to produce quicker, faster, cheaper. However, at the same time, producing better quality designs. So what does BIM give you? What does building information modeling give you? Well, it gives you control. It may be worthwhile just referring, it's something that Simon very, very quickly touched upon. Within his presidential address, Norman Train, who's now the new president of the Institute of Structural Engineers, said in his address, he said that structures can be sophisticated, eloquent and economic, but if it's late, ambiguous or difficult to construct, it will have failed. I just wonder how many buildings do actually fail because of that reason. If we look at the information content where techless structures can be used, it can be used all the way through the complete phase, from original linking to architectural sections, conceptual design, linking to A&D products, production of generation drawings, multi-material detailing, production of drawings and reports, manufacturing information. As like Mark said, we can download from the steel machines, the CNC machines, to physically make the steel work. Or for reinforced concrete, we can actually go to the bar bending machines that bend the reinforcement for delivery to site. We can go through erection schemes and then finally site arrangements and site handling itself. If you look at the technology steps, obviously years ago, everything was drawn by hand. We've gone through the drawing by hand stage, and we went to the 2D stage where computers were actually used to production of information. But that really was just electronic drawing boards. We then, in the mid-80s, we went through the 3D side, obviously the third dimensional approach where you get X, Y, and vertical information and production of that information. And we're now into a stage where we call it 4D, the fourth dimension being time. And this is all encapsulated in the BIM model itself. Oh, I get a whistle somewhere. Okay, as you can see, the various stages of the industry, we're saying that the steelwork industry has gone through the 3D into the 4D. Concrete design is just really going from the 2D side into the 3D environment. So we said before, what is BIM? Well, in many ways, BIM can be explained as it's what CAD was originally intended to be. In other words, I have an object in my hand, and it's changing that object to the different systems. So whether it's a structural system or whether it's an architectural form, the boundary representation of that member, together with all the attributes, can be passed across. So that can be shared between different systems. Again, BIM can be explained in another way. In every project, an architect will produce a scheme, and he passes a certain amount of content across in the scheme by drawings, but he's worked on a whole wealth of information that's never passed on through the contract. Again, the structural engineer can produce more information by drawings, but he has a wealth of information in the background that's never really tapped upon. Again, the contractors, whether it's a steelwork detail or it's a concrete contractor, or even on site, a wealth of information is actually lost. If as-built drawings are produced, a bit more information can be passed across. But if people are using the common BIM information, everyone is building upon that information, and everyone has access to other people's information. So what it really comes against, instead of the old-fashioned 2D way of drawing where you have a line, you don't know if the information on that line is correct, you have the model. And the model of the structure is built for the very first time in the memory of the computer. So it's built before any materials are involved. So you can do your class checking in that kind of environment when it's very cheap to change. Again, people talk about the structural BIM as against the architectural BIM, but there's whole concepts of BIM. We have the whole BIM of the building, whether that will include the architectural, the HVAC, electrical and plumbing information, but also the structural information. Techless structures just concentrates on the structural components. So there we are looking at the structural engineering, we're looking at the steel detailing, the concrete detailing, the timber detailing, and all that's contained within one common Tekla model. So linking of best-of-breed applications. The engineer wants to start modelling the interfaces, so he needs to have access to the architectural model. He needs access to the MEP model, the mechanical, electrical, or plumbing or piping, depending on what you want to call it. But he needs to have this information. And what we actually have here is an architectural model. This one's been produced in ArchiCAD, but it can be another of the applications. And the engineer can just import this into his model just by using an IFC, an industry foundation class. And again, we'll come on to cooperation and different types of environment and different standards. But it's a means of getting that information across. Likewise, it could be an MEP model. And this model then can be passed across to the engineer or back to the architect. So everything can be class checked in the different products. Again, it could be that the engineer wants to have links to his analysis and design systems. And this can be done in the same way. This is a model that's been produced in Tekla Structures, and the physical members have been changed to analytical members for passing across to the A&D products. It really wants to be pointed out the advantage here that what we have is an MEP solution where normally done for plumbing and for ductwork, etc., and for mechanical parts. And the engineers working on the MEP scheme won't have the tools to create the structural model. So they're not modeling this kind of information. And here, the stadium roof has actually come through from Tekla Structures. So you can import it into the MEP solution. So that you can do your class checks on the structural side or the mechanical side. Okay, we started talking about collaboration, and what I really wanted to do is to spend a few moments on talking about how we can get information across. We started off with the IFC, which is the Industry Foundation Classes, which has been pushed by organisations like Building Smart, used to be the old International Alliance of Interoperability, and it's a means of defining the boundary representation of these objects and passing it across. The reason why IFCs are very strong, it's for all building objects. So whether it's an architectural object or a structural object, it can all be defined. Again, we have links through the .NET, and is anyone familiar with .NET programming? No, okay. Microsoft have a Visual Studio, and what it allows you, within Visual Studio, it allows you to have 32 languages of choice, and you can pass this information across. So I can write something in C#, you can write something in Visual Basic, and it can transfer the information as an object. We also support industry standards like CIS2, the Steel Detailing Neutral Format, DSTV, and these allow us to talk to different products like Intergraph's PDS, Intergraph Smart Plant 3D, or Aviva's PDMS. We can go to the CAD MEP system or through ArchiCAD, just using standard industry standards. So we can Okay, if we just have a quick look at the Open API, the application written on the top, as I was saying before, with the Microsoft .NET Studio, we can have different languages. And all I've done on the top is, within Tekla Structures, I've defined some objects, and I've created this small program in Visual Basic. Again, the user defines the spans of the building, the number of bays, the story heights, where they want the splices, what he wants for a slab, where he wants the position of the building to be, whether he wants foundations in there. And they can just fill in the information, as we see here, and then just fill in the spans, and then change this information, and then just generate the whole structure. Well as going across to a proprietary system like that, you can also use Excel as a trigger. So you can use Excel by filling this information in, the size of the members, the grade, the start position, the end positions, and you can really write this information so you press the button and a structure is produced. What .NET is allowing you to do is to define or tailor the system to make a bespoke solution for your own requirements. Again, we may want to look at the information review, and this is really where we're taking across this BREP information. I've taken here an MEP solution, and what you can do is compare it with the structural solution. This structural solution has got all the openings and the perforations between the slab, etc., of where these pieces of duct go through. And what I can do, I can put the two models together. And I can do the clash detection on the structural side or the mechanical side, and I can get more information on here, and I can actually go into any of those objects, click on it and inquire on it. So it's a pump, I can tell the manufacturer and where the information came from. But I can also compare the models. I can look at the new file, I can look at the existing file, I can look at the unchanged objects, I can look at changed objects, I can look at items that have been deleted and items that have been inserted. So I do have the whole control on the two interfaces. Again, the control can be done through the model organizer, and in this case I can look at a section A of a building, and I can go across and zoom in on the second floor. And I may want to start looking at the various parts, and I may want to start looking at the wall panels in this particular area. And I can zoom down to these areas or other classifications and put together other reference models. So you have these customizable panes of control of information. Again, if we're looking through the 4D information, and the fourth dimension being time, I can very quickly go across to scroll through the second floor. I can then start looking at the different areas. In this case, I'm going to look at the hollow-core slabs. And I can just concentrate on that area. Again, you can see I have a timeline here. I can fill that information in with further and better information. Also, as before, I can dump all this information out to information use existing like Microsoft Project. So the whole control is actually through the BIM Manager. Again, people will ask, well, what kind of projects can be done within Ctbuh Structures? And it's industrial buildings, cladding, stadium work, commercial buildings, offshore buildings, miscellaneous steelwork, towers, metal framing, pre-engineered buildings, or bridges. Again, that's mainly on the steelwork side, so we can look at the concrete side, and we have a wealth of information. These examples here are projects that are ongoing at the moment in Finland. If we look at the Nestle Oil biodiesel, which is one of the case studies, and it's not a tall building, but it just shows you what you can do with the system. This biodiesel refinery is actually in a place called Ctbuh over in Finland. The systems used on this was Intergraph's PDS, and Ctbuh Structures was used. The products, or the plant itself, is actually a €10 million scheme. There's 1.5 million man-hours for the engineering, and there's 3 million man-hours on site to construct the project. If I show the model and some of the photographs from on site, the building covers about 13,000 square metres. There's about 19,000 cubic metres of concrete and 5,000 tonnes of steelwork. And there's approximately 200 kilometres of pipework just in the main stories, or the main plant itself. Again, it's not only plant structures or tall buildings. This is an example of the Swansea Sail Bridge, which in the UK, it won a design award a few years ago. Again, the whole structure is modelled, and the drawings can be produced automatically or semi-automatically. And if you change something in the model, all your information, all your reports, and all your drawings are automatically updated. Again, if we start going to more of the urban habitat, if you start looking at stadium-type projects, this project is the Wembley Stadium, which football supporters in the room may recognise. The building itself, the main stadium itself, has some various views there. And it was really defined into 4 stages. There was the arch, the bowl, the parametric perimeter truss, and the main roof itself. There was about 23,000 tonnes of steelwork in the job. It was actually subdivided into 160 phases, and at the end of the project was brought back into one master model. Just very quickly looking at the scheme, there's about 2,500 intersection points. Each intersection point was actually modelled down to 8 decimal places of a millimetre. So you're dealing to 0.000001 of a millimetre. So you can see it's more like mechanical tolerance than normal structural tolerance. But they're needing that kind of accuracy because of the slope of the build, or slope of the structure itself. In the arch, there's about 1,700 tonnes of steelwork. The diameter of the arch is actually 7.4 metres. And at 315 metres span, it's the largest single span roof member in the world. The bowl is about 15,000 tonnes of steelwork. Again, there's 90,000 seats in the structure, and there's no vertical supports above the terracing. So it means every spectator has got a complete uninterrupted view of the pitch itself. The parametric perimeter truss was about 14,000 tonnes of steelwork in there. Again, that was actually used to transmit the loads from the roof and from the arch into the main bowl itself. And the roof is about 4,500 tonne. It may be worthwhile saying that there's actually a sliding roof on this area here, and it's erected on 6,000 tonne of temporary steelwork to erect the main roof itself. Davy Scott was in the building before, but it may be worthwhile some projects on the London landscape. You can see obviously the Swiss rebuilding, 24 St Mary's Axe, and there's the structure behind the building itself. Again, a couple of projects that are going on at the moment. We have the Heron Towers that just started, together with the Leadenhall project. Again, all modelled by Arups and passed on to the steelwork contractor in this case. A building to look at a bit more closer is the 51 Lime Street. It's now known as the Willis Building. It's the fourth tallest building in London, in the financial district. It's only 29 stories at the back, and it tapers down to a 60-storey block at the front, and the 10-storey block linked together by two basement buildings. Quite a complicated structure, as you can see from the various elevations. Again, a bit more interest on the building. The models itself was actually created by Whitby Bird, and it's passed on to William Hares, who are known quite well in India as well, a global steelwork contractor. And the architect, Foster's, and the construction manager, Mace, realised that the only way to get the true information from the model was to actually use the model itself, and that's what they were doing at the end of the project. A couple of areas to look at. They had what they called the sawtooth construction. If you imagine all these members are all curved, and you can see that where the glazing mullions go onto the side of the building, which is supported by these permanent soffits, obviously the geometry is very, very complicated, and this is the kind of information they needed to get from the model itself. Again, they also had what was called the Lancashire columns. This is a double two-storey height column, again for fire engineering, consisting of 140mm plates, 100mm webs, toe plates, all in a steel tube, all filled with concrete to react to any kind of fire loading. And that is the final structural scheme. Again, you can see the complexity of the structure itself. Every spare square metre on the project was actually utilised. We can also see another quick case study, a building over in Broomfield, Colorado. Again, it's really a case study that can be downloaded from the various websites. It's only an 11-storey building with one basement area, but the case study was actually used to produce the way of working and really cost savings on the project. And that's the case study or the white paper itself. What was saying before, the steelwork and the reinforcement can be positioned. So here we have all the reinforcement on the job in one particular area, and you can see the actual work on site. So the model is no different from the actual work on site, and that's how the whole thing is coordinated. Again, BIM was actually used in all the site meetings, and you see here one of the discussions actually going on of how the information can be used in placements. And what we actually have, if you look at the steel frame was actually delivered 40 days ahead of schedule. There was actually 550 detailing hours saved on the project from the original estimate. The fabrication period was reduced by 5 weeks, and only 2 requests of further information were required on the whole of the project. On the concrete side, there was 0 RFIs. They reckon that the schedule on the concrete placement was reduced by 2 weeks, and there was a 21.6% reduction in reinforcement because they knew where every bar was going to be placed. So as a quick overview, the total cost savings on the whole of the project, the steelwork, they saved $229,000. The concrete, they reckon they saved $113,000. That doesn't include the indirect costs for completing the work early. Some other projects we could start looking at. We started talking about stadium projects. This is the Beijing Olympics from last year, what was called the Bird Nest Stadium. People say it's a very, very complicated stadium. Well, it is because the architect decided that every member is going to have the same size. It was only the wall thicknesses that changed. But what people don't really realise that where a column started on the outside as a flange, it actually twists over the top. So it actually turns through 90 degrees. So as well as going over the top, it actually rotates by 90 degrees. So the geometry is very, very complex. Again, another building that's actually used around the world now by cable television, by the CCTV. This was again used by the TV for broadcasting the live pictures around the world. And you can see the CCTV stadium. If we come back to our original case study, again produced by another one of our users, the Shanghai World Financial Center. I realise that Mark's going to ring the bell in any minute now, so I'll be very, very quick. There's a very quick overview of the structure. Again, it's on most of the boards outside. It's also in the top 4 buildings, depending on different classifications. The building itself was actually a $1.1 million project, and the building is actually 492 metres high. It's restricted by that height by planning requirements. Originally, it was planned to be over the 500 metres, but the local authority permit wouldn't allow them to go any further. But again, there's 3 basement levels, there's 101 floors. It's a mixed usage, and there's 30 escalators and lifts in the building itself. So in conclusion, what is BIM? Well, BIM is more of an activity than just one particular process. It's a means of actually allowing all the project design team members to collaborate all the information and also to clash check other people's work. BIM is probably well known in the AEC, the Architectural Engineering and Construction market, but the same process is known as interoperability in the plant market, the EPC market. So using industry standards and open APIs allows the objects to be transferred from system to system. So things only need to be modelled once. The BIM concept can be used from conceptual stage right the way through the design, detail and procurement and manufacture. And projects can be total designed, measured and coordinated and controlled before works even starts on site. The site coordination is always required, and this also can be controlled through the BIM model itself. So if you need any more information on Tekla Structures or the BIM process, just see our website, which is www.tekla.com, or we do have a stand outside, so if you want any further details, etc., just come down and have a word with us. Thank you very much for your time.